Hello and welcome to another lecture on natural science. Today we're doing lecture K. We're in week 6. We're beginning physics and we want to talk about the topic of light. Let's discuss some vocabulary words here. Luminous is a word to describe any object that gives off light. These can be light bulbs, stars, including the sun. Okay, we wouldn't really call like my shirt luminous because it's reflecting the light of the fluorescent light bulbs in this room. So don't confuse any kind of colored object as luminous. You know, your car might have color to it, but it's because the sunlight is causing only a blue color to reflect off of that, for example, or only a red color to reflect off of that. So that's why it appears to have a certain color. Okay. We're familiar with a light stick, for example. That would be a chemical example, a glow stick. Your cell phone, you can operate it in complete darkness, assuming the battery's good. There's organic light emitting diodes in there, or OLEDs. Many of our lighting in our houses are light emitting diodes. There's certain colors emitted. When they mix, they form like a white light. So that's why it's kind of like a white light in this room right now. Okay. Now I want to talk about incandescence. Incandescence is the adjective, right? And incandescent would be the noun. The filament within the old style light bulbs, if it's heated up to a high enough temperature, it glows. Usually it's tungsten. And let me just show you an example of this over here. Okay, so a combustion reaction. I'm not sure if you can see this in the video with the black background of the countertop, but a combustion reaction is luminous. Fire, right, produces light. Light, as we'll see, is a form of energy, and I'm gonna take this small little wire here. It's got, not sure if you can see this against my hand maybe, but there's a little circle at the tip of this wire. And I'll heat this up to a very high temperature. And I'll bring it over to the to the camera. And let me bring the camera closer. So when this wire is placed into the fire, it heats up to a very high temperature, and it glows a red color. Okay. A iron poker in the fire, for example, would also be an example of a luminous object. Okay. So obviously, an electric current is what's used to light up light bulbs. Current is passed through the wire, has resistance, it heats up to a very high temperature, and it just emits different colors of light. Now, we have this concept of black body. Well, let's talk about the electromagnetic spectrum first. Light is a part of the electromagnetic spectrum. it's radiation, okay? When an object emits energy in the form of particles, we call that radioactivity, or alpha emission, beta emission, gamma emission, as we saw previously. Gamma rays are a form of light, actually. Visible light, I should put visible in front of this, is a part of a very continuous spectrum called the electromagnetic spectrum. And electromagnetic radiation, again, should not be confused with only radioactivity. It's anything that emits light, reflects, or whatever. Let me show you what this looks like. This camera is pretty blurry, so let me just annotate on top of this, okay? So we have different labels here. There's gamma rays, X-rays, UV, visible light, infrared radiation, microwaves, radio waves, and long radio waves. So let me write those on top in case you can't see that well. Okay, we got gamma rays. I'll just say gamma. These are X-rays, okay, up to this point here. X-rays, as we've talked about before, pass through the human body well. They are stopped by bone, so that's how you can image, ribs and skeletons and things like that, okay? The skeletal features. UV stands for ultraviolet light. It's beyond the ability of humans to see ultraviolet light. Some insects can see UV light. For example, bumblebees can see UV light, and presumably it helps them find flowers or nectar a little bit better. This small little sliver in the middle of the electromagnetic spectrum is visible light. Okay, so when you think about the sun, for example, or other chemical reactions or whatever, there's many different areas of the electromagnetic spectrum that can release light or absorb light or interact with light in some way. The human eyeball is a very complicated sensor that only detects this very small sliver of electromagnetic radiation in the middle of the whole thing here, and it's called visible light. And then the way to remember the colors of the rainbow is with Roy G. Biv. I know it's written backwards here because we're going from X-rays to radio waves, but if we flip this around, it would be in order. But the colors of the rainbow are these 7 different colors. Isaac Newton divided the colors, the spectrum of visible light, or the colors of the rainbow, into 7 colors similar to the octaves of a piano, for example. So there was no real reason for doing this, but he liked the symmetry, he liked music, and sound and light are related in a way. But anyways, so that's red, orange, yellow, green, blue, indigo, violet. When I look at a rainbow, I see the red, the orange, yellow, the green, and then just kind of blue or purple. But these are distinct regions that are spread out in here. Okay, blue is kind of like a blue sky, and then indigo is kind of more purplish, and then violet is very, very purple. So our eyes don't have very good sensitivity down there by the violet. Beyond this would be called ultraviolet. Okay, so a frequency beyond violet would be called ultraviolet. Okay, so we call this just visible light. IR stands for infrared. infrared, and that's beyond the red, okay? So IR is not visible by us. It's heat. So if you, for example, go to a buffet and you're reaching underneath the glass shield to get your food, and then you feel like an extreme warmth there, that's kind of like lit by a dim red light or something, that's a heat lamp. It emits infrared heat, okay? Those lights are also used for, you know, if you need to hatch some eggs. If you're having chickens in the spring and you just buy the eggs and you want to hatch them from eggs, the little hatching light will be infrared. Your body emits infrared heat. We are warm-blooded creatures, right? And we emit heat. And night sensing cameras can detect that. The infrared light can also be seen by a pit viper. Pit viper is just a snake, lives in the desert, and even if there's no moon, they can detect the heat of a mouse that's running across the sand there, okay? Just because of the infrared radiation that people are releasing, or a mouse is releasing. Microwaves are next. We are familiar with microwave ovens. When I was a kid, microwaves started becoming used in the United States, and people wanted to know how they worked. So they bring scientists into the television studio and interview them on the news and all that. And they would tell them, microwaves is a part of the electromagnetic radiation. And everybody heard the word radiation, and they freaked out. They misunderstood the term. They thought that microwaves use radioactive elements. It's radioactive, and it makes your food radioactive, and it's unsafe to use a microwave. When I was a kid, we would play on the fears of our aunts and moms and stuff like that by saying, hey, nuke your burrito for 30 seconds. And that's my generation that started that. So if you need to nuke something, that means slang for a microwave something. And microwaves are, of course, used by your cell phones. That's the radio that's used for communicating with the cell towers. Your Wi-Fi, if you have a wireless Wi-Fi in your house, that's using microwave frequencies, okay? Radio waves are just the remainder here on the right. You have something called long wave, short wave, ham radio, maybe FM or AM, these different terms over here in the microwave and the radio regions. Don't worry too much about that. Just know that that's radio waves, okay? So radio waves obviously are used for radio and television. If some studios still transmit on those frequencies, I'm not sure. And very rarely satellites, they use much higher microwave frequencies. So anyways, that's in a nutshell the electromagnetic spectrum. The visible part of light is this small sliver in the middle that our eyes are sensitive to, okay? As I previously demonstrated, a heated piece of wire is incandescent. It emits light of various frequencies, and the frequencies of light, or the wavelengths of light, or the color, let's just call it the color of light, is going to vary depending on the temperature, and that's depicted by a black body radiation curve. A black body is not black. It could be like the sun. It could be something very bright, or it could be an asteroid that's just very cold in space. Everything emits radiation depending on its temperature, okay? It could be very cold or very hot, like the sun, but all of these objects are going to be emitting electromagnetic radiation in some fashion. Maybe it's visible if it's in a fireplace, maybe it's invisible like the human body that's emitting infrared light, okay? Or the sun might be emitting some ultraviolet light. And so let me show you the curves of what these look like. Okay, here's a nice little graph, and it's showing these red curves here at different temperatures, okay? And the temperature units here are in Kelvin, okay? So let's pick the middle curve here, which is 5,000 Kelvin. I believe that's the approximate temperature of the surface of the sun, and it's the approximate temperature of tungsten filament in the old style light bulbs, okay? And obviously, if you heat up a filament to the same temperature of the sun, it's going to emit the same type of radiation as the sun, so it's going to have the appearance of sunlight inside of in your closet as you turn on the light, right? And you look around for things. So if we look at this curve, we can see how it kind of makes a bump here, and then it goes down very gradually to the right, okay? It's labeled here. On the left in yellow is ultraviolet light, in the middle is visible light, and on the right is infrared light. Remember, infrared light is heat. So an old style light bulb, an incandescent light bulb, is going to be very hot, okay? If it goes out, you shouldn't reach up just to unscrew it, because you're going to burn your hands. Now, I'm not talking about the current LED lights that we have in our houses that are very cool, okay? You might have one of these on the porch outside your house. It's very hot, okay? You definitely will have one of these in your oven, and you'll also probably have one under the range if you have like, you know, a fan to remove smoke from your kitchen, or maybe an under microwave light, okay? These are hot. They emit light in this fashion, okay? So you can see how the curve is pretty much a maximum in the visible light, and then as it goes down, it's emitting quite a bit of infrared light, okay? Sunlight emits warmth, okay? So we know that we can see light when the sun is out, but also we feel very warm when we put our hands out in sunlight, or we let the car sit in the sunlight. It seems to get very warm, right? Because a lot of the radiation is given off in the infrared regions of the spectrum. There's also ultraviolet light given off by the sunlight at 5,000 Kelvin, because we know we can go out and we can get a suntan that's caused by ultraviolet light. We can get a sunburn that's caused by ultraviolet light, and people can get skin cancer, unfortunately, which is a wavelength of ultraviolet light. Now, we do have a layer of the ozone that helps protect a lot of that ultraviolet light, but some of that still gets through and can give us a tan, even on a cold, you know, a foggy day, or even a day that has cloud cover, okay? So you might look outside and say, oh, this is a great day to work in the garden. There's a bunch of clouds out there. I'm not gonna get sunburned. Think otherwise. You can actually get sunburn on a cloudy day, because ultraviolet light can penetrate through clouds and, of course, interact with your skin and give you a sunburn or a tan. If we have a lower temperature, okay, that's 4,000 Kelvin, you can see how this curve shifts to the right, okay? So lower temperature, this curve is going to shift to the right, and that means it emits more infrared radiation. I'm just going to call it IR light. So the human body, we're nowhere near 1,000 Kelvin. We're at like, you know, 300 Kelvin or so. We're very small, very low. We emit mostly infrared light, okay? Things in space that do this might be like a brown dwarf, okay? It's a planet that's a failed sun. Or Jupiter, for example. Jupiter emits quite a bit of radiation in the infrared light. If you want to take cool pictures of Jupiter, one way of doing that is put a special filter on your camera or your telescope and take it in infrared light, and you'll see interesting banding features of the clouds and so on, okay? If you increase the temperature, higher temperature, this curve shifts to the left, you're going to have more UV light. Okay, more UV light. So this is black body radiation. Black body, once again, means that the object behaves ideally and emits light with this kind of distribution, okay? Most objects are ideally black body emitters, and things like that wire in the flame, your body, the sun, stuff like that are generally, for the most parts, considered to be black bodies, okay? It's just a term that I don't want to get into, but anyways, that's the curve for that, okay? Now, you have different types of emission or absorption. Emission is when light is given off a laser pointer, for some reason, might emit red light or green light, depending on what kind you have. Okay, a glow stick might emit, you know, red or blue or yellow, right? Depending on what kind of glow stick you have. And your cell phone, you know, depending on what you're looking at, might emit different colors as well, right? So that's emission. And it turns out different atoms of different elements emit light when they're excited. We'll get into this in a second. Absorption is the reverse of this process. Absorption is when light is absorbed. So this screen is pretty black here because when the lights hit this, it's fully absorbed, okay? This wall over here on the right is blue. It seems to absorb all of the colors except blue, which is reflected off of that, okay? So this wall absorbs the complement color of blue. We won't get into the art of the primary, secondary colors and complement colors, but basically you draw a circle and you write red, orange, yellow, green, blue, indigo, violet on there, and then you see what's opposite the circle, okay? So opposite of blue is gonna be what, right? So you look at that and you can see what this wall is absorbing, okay? Elements have characteristic emission spectra. They emit only certain wavelengths of light. I'm just going to say colors for now, okay? We don't need to focus on wavelength and frequency and energy at this moment. So colors, okay? So fireworks, for example, are made possible because some elements emit red or blue or green or yellow or purple or white. And so you can craft the pyrotechnic mixtures of chemicals in there so that when they explode and then they scatter their burning contents through the sky, you can see a beautiful star formation of red or yellow, okay? So that's because of certain elements that are existing in there. Let me get my flame up here again. And this should be readily apparent even far away on the camera. So I'm going to dip this wire into one of these solutions here. I'm going to do barium here. And I'm going to observe the color, okay? Does everybody see a greenish color there? Looks a bit yellow on the camera. Okay, so Another color that I would like to show you is sodium. Sodium is quite vibrant. I need to put this down so I can get the solution. All right. This will pretty much contaminate my wire and I'll have to clean it for a long time. That's the color from sodium. It's kind of like this yellowish color, okay? Lithium would be red, copper or barium would be green, aluminum would be white. So this is how we can control the colors of fireworks. Okay, let me just write that down here. Potassium is like a purple or a lilac. Okay. Lithium is red, and so on. Okay. And so when these chemicals here in the lab are combusted or burned, they emit light of only certain frequencies. Astronomers can go and look at stars, pass the starlight through prisms, and then they can look for components of lilac or red, for example, and then characterize and understand that, oh, these elements are on this star. So we know that there are carbon-rich stars or oxygen-rich stars or so on and so forth. Or we can look at the light reflected off various moons or planets in the solar system, and from that data we can get information about the light that is being absorbed or emitted from the atmosphere of Titan, which is a moon. So anyway, something like that is a very useful tool, okay? How does this work? First and foremost, let's remember that electrons are negatively charged and protons in the nucleus are positively charged, and opposites attract. This means that since opposites attract, the electron and the proton like to be as close to each other as possible, and that's called a ground state or a stable state or a lower energy configuration. So we'll do the nucleus here in a light blue. We don't really care about the protons and neutrons right now. We're actually focusing on the electrons, okay? So let's talk about an absorption process. I'm going to draw some rings around this atom here, okay? And I'm going to draw an electron in one of these rings or orbits in a gray color, okay? I'll just put well, I think I'll just put one, okay? We'll keep it really simple here, okay? So this might be hydrogen, okay? Hydrogen has one electron. There it is. Now, if you excite a hydrogen atom by 3 different ways, right? You can burn it, you can use electricity, or you can shine a laser on it, or other kinds of energy like light. So you excite this by adding energy. Electricity works well, right? You could pass a current through it, plug it into the wall or something. Anyways, and what happens is this electron can absorb energy or absorb light. Okay, so here's light coming in. And what's going to happen is the electron is going to be excited to a higher energy state. Okay, so this configuration right here is called a ground state because the electron is in the inner orbit closer to the nucleus. So the electron is closer to the nucleus. We say lower energy or more stable. Lower energy is always more stable, okay? So if we were to shine light on this, some of the hydrogen atoms could absorb that light, that energy, and the electron could be promoted to a higher energy state, which we call the excited state. And I'll fit it in up here. I'm going to draw my orbits here again. And I'm going to draw a little electron as a ball on the outer orbit, okay? And this right here is called an excited state. This process is called absorption. What exactly is the atom absorbing? It's absorbing energy. Okay, I wrote energy here. It doesn't have to be light. It can be, you can put it in a fireplace and it could absorb the energy just from heat, or it could be electricity, or it could be light. Okay, so energy could be light, electricity, or heat. All right, the excited state here, let's define this carefully. The electron is further from the nucleus. And remember point number 3, opposites attract. So what we have here is an attraction between an electron and a proton. And here we're making them far away. So it's going to be higher energy, less stable. So let me box this term excited state. Think about just the idea of this everyday language, excited. When you're excited, you have lots of energy. So what are you going to do with that energy? Maybe you're going to go out with your friends. Maybe you're going to mow the lawn. Maybe you're going to tackle that project that you've been putting off. Who knows what you do with your excitement, right? So what is this atom going to do with its high energy state? The electron can spontaneously fall to a lower energy orbit. It's going to look like this. And that process is going to be emission. So over here, let's talk about the emission process. We want to draw an excited state, which we've described and defined. And then we want to draw a ground state that we've described very carefully. Okay. So we got the nucleus again, which has the positive charge. Let's draw a couple of rings around this. Okay. So what are we starting out with? We're starting out with an electron in an outer orbit, and that's the excited state. And what's going to happen is that this electron is going to fall down or transition to a lower energy orbit. That energy has to be released somewhere, and it's released in the form of light. Yes, it can be heat, light, or electricity, but here we're just going to pretend like it's light, okay? So let's draw a little bit of a wiggle. This is light that's emitted, okay? So this is called an emission process. And that's why in the flame, we saw sodium burn bright yellow. Barium, it looked to be like a greenish color. Excuse me. So that's emission. Lithium would be red, and so on and so forth, okay? So that's what's happening in your fireworks. You're exciting atoms with heat. There's chemical reactions in there that produce a tremendous amount of energy in a short amount of time. And some of these atoms become excited. The barium, the aluminum, the potassium, whatever. When those electrons transition down to a lower energy state, they emit the beautiful colors of the firework, okay? So that's how absorption and emission work with atoms. all right? Now, most things aren't on fire and producing colors. We have, you know, labels and things like that that are blue, red, white. You know, how does that work? All right. Well, you have a couple different types of reflection. Okay. You have reflection off of a smooth surface. Okay. Let's think about the smooth surfaces that reflect light. Your bathroom mirror, a window. Maybe the window of a car is turning and it just catches the sunlight and it like hits you, right? So it could be glass, or it could be a very tranquil pond, okay? The surface of the water on the pond, you can actually see the reflection of trees and things like that in it, okay? When this happens, let me just drop down here. You have light that comes in, okay? And because the surface is very smooth, the light goes out without any distortion, okay? So that's on a smooth surface, okay? Light rays come in parallel, and then after they're reflected, they go out parallel, okay? Let me see if I can, hold on just a second. All right, now we have diffuse reflection that happens off of a rough surface. So first we call it a rough surface. Okay. And we call this diffuse reflection. Let's draw a little picture of a rough surface. When light interacts with this, the light that comes in initially parallel hits this rough surface and is scattered in various directions, okay? That could be anything. A tree, it could be a leaf on a tree, it could be a tree, okay? It can be a diffuser. Those of you in photography know that you have these little, they kind of look like umbrellas, okay, that are made of white, you know, silk or cotton fabric, and then you have a flash in here that illuminates the underside of the umbrella, and then because of the diffuse reflectance, it spreads the light out more or less evenly, okay? If you pointed the light towards your the people in the portrait, it would cast a very hard shadow, okay? You would see shadows and very strong features in the face and so on from that direct light. So this is a technique used in photography, okay? So the tree, many things like, you know, usually floors, which have been scuffed up and everything. You can't see a perfect reflection of something in there unless it's like a really good waxed floor or something, okay? So the idea here is that bundles of light are reflected diffusely in all directions from every point on an object. Only a few light rays are shown from only one point of the tree. If your eyeball is here, let's draw a little stick figure here, and you're looking in this direction at the tree. It's not going to blind you, even though the sunlight in white here is illuminating the tree, because only one or a few of these light rays are coming towards you, okay? So that's nice for diffusion. if this was a mirror and the sunlight was hitting it, you would be blinded, right? You'd have to guard your eyes or look away. All right. Let's now talk about the law of reflection. Okay. The idea of reflection implies symmetry. Okay. We have a couple of different vocabulary words to describe this. Okay. So here's our smooth surface. We usually say it's a mirror. The incoming light is called the incident ray. And this word ray, we kind of understand the context from the English language in terms of sunlight or something. We know that if there's a certain parting in the clouds, we can actually see a sunbeam or a beam of light coming through the clouds in a very narrow beam, okay? Kind of like a flashlight. These rays are perfectly parallel. They're not spreading out really fast. It's just like a beam that comes straight through. And so that's what we indicate here with a single line, and we have an arrow on top of that line showing the direction that it's going. Okay, so this is called the incident ray. Now we have something called the normal. You're going to hear me describe light rays in respect to the normal. The normal is basically a line that comes off straight off that object, okay, perpendicular to that object, okay? So let's say the bottom of this frame here is the mirror, okay? The normal is just going to be straight off that, okay? It's not going to be at an angle like this or like this. It's going to be straight off. The angle there is going to be 90 degrees, okay? So this is called a perpendicular. I'm having trouble with spelling here. Perpendicular line with respect to the mirror. And it's imaginary, okay? No light is coming in or leaving at that point, okay? Now we have something called the reflected ray. Angles are a little off there. Let me fix that. Okay, that looks better. So in blue here, this is the reflected ray. And this is the outgoing or the reflected, ray. So this is the outgoing ray of light. And I should mention here, it doesn't matter what color the light is. This works well for red, orange, green, indigo, whatever the color, okay? Now the idea here, okay, so we have this angle here. Let me just call it I. Okay. So that's an angle is defined as between two lines. Okay. So an angle like that would be 90 degrees. An angle like that might be 45 degrees. An angle like that would be 0. Okay. So this is just an angle. The angle of incidence. And it's with respect to this imaginary yellow line, which is called the normal. This angle here is called the angle of reflectance. And what is the law? The law basically says the angle of reflectance is equal to the angle of incidence. Okay? So the law states the angle of reflectance is equal to the angle of incidence. I'm just going to write R equals I here. Okay? So that's the law. So for example, if we have a mirror, and I'll use light again so we can, so first let's draw the normal here, okay? And if I have a light beam or a light ray hitting that point, how is it going to be reflected? Okay, let's look at maybe some choices here. Would it be reflected this way? That's choice A. Would it be reflected this way, which is choice B? Would it be reflected this way, which is point C? Or maybe this way, which is point D? Okay, so what you need to do is carefully look at the angle of incidence. That's basically this angle right here. So oftentimes we use a curved line to indicate, you know, how big that angle is between those two lines. Okay, it's about this. Okay, so there's my protractor. And now I want to take it from the yellow line and see which one of these lines match up. It's going to be that angle here. Oops, that angle here. So it looks like angle C is going to be correct. Now, also the law states that it's going to be reflected away from the normal, okay? So if this incident ray comes in, we know it's going to be on the opposite side of this yellow line because that's the direction of reflection. Most of this is common sense, but they had to state it and prove it and study it and see that, yes, I measured it and it works for red light, blue light, and so on and so forth, okay? So that's the basics of that situation, okay? So reflection is pretty simple. We won't look at different mirrors that are shaped in a convex or a concave fashion. We're just going to look at a flat mirror, okay? Now, what about refraction? Refraction basically means bending light. When light passes through an object, like a lens, it's going to bend, and that's how eyeglasses work, okay? When light passes through the plastic or glass of our different glasses, it is bent in certain ways to correct for deficiencies of our eyeball that distort the image, okay? So here's my definition of refraction. Light bends when it passes from one object, such as air, into another object, such as glass. So it could be water, it could be anything that light can pass through, okay? So let's take a look at this in a little bit more detail. So what I'm drawing here is air on top and water down below, okay? And we're gonna look at what happens when light passes into this system. So once again, we're gonna have the normal. Okay? we have the normal, and remember the normal is perpendicular to the surface, this point right here, okay? Now, when the incident ray comes in, let's label this incident ray. And let's label, well, it's labeled normal there, okay? We would normally expect the light to continue on this path and travel in a straight line, okay, on this dotted line here, okay? That would be the expected trajectory of this ray of light. Okay? But that does not occur. What happens is the light bends. And when it bends toward the normal. Okay, bends toward the normal. So let's use a blue color here, and instead it's going to go in kind of this fashion here. Okay. This is called the refracted ray. These angles are different, okay? This is called the incident angle, and the angle of incidence. Let's use I here to label it. Angle of incidence. And we can see that when it's refracted, the light bends in this fashion, and we have the angle of refraction down here. These two angles are not the same, okay? I'm sorry, I messed up the label here. It should be on the left towards the normal, so the angle of refraction should be here. So it's smaller, okay? Here it's greater, and then when it bends, okay, it gets a little bit smaller there, okay? So this is a ray diagram showing refraction at the boundary of air and water as the ray moves from air through water. And note that the angle of incidence does not equal the angle of refraction, okay? And this is because light bends. That's what's observed here, okay? All right. What if the opposite happens? What if we have glass and we have air down here? So here's the normal once again. It's that line that's just perpendicular to the surface. And here we want to have a ray of light. Maybe it's inside of our glasses already, and it's traveling kind of like in this direction here. And it's going to impact the interface, okay, where the glass and the air meet. So that's called the interface. So the ray of light's coming this way and it's going to hit here. How will it bend? Again, so as we change from one medium or one object to another object, we are going to expect this light to bend. We do not expect this light to continue on the path. because glass and air are two different objects. Glass is more dense, air is less dense. So because of the density change, the light is going to change, okay? So this is just a straight line. It's not really expected. We know now it's going to bend. How does it bend? Does it bend away from normal or to the normal? Well, here, what's going to happen is it's going to bend away from the normal. So in blue here, I'm going to show it going in this direction, okay? So let's label things here. This is the angle of incidence, and this is the angle of refraction, okay? And here, once again, the angle of incidence is not equal to the angle of refraction because it bends, light bends, okay? Okay, so let's try to analyze what's going on here and why the two figures are different. Here in this image, we have the ray of light going from glass to air, and for some reason, the light is bent away from the yellow line, which we call the normal. It's bent away from the normal. In this situation, we have air, light, incident ray coming from air, right? Going into water, and for some reason it's being bent towards the normal, okay? So the idea here is that water is more dense than air. Okay? It's going to be shifted towards the normal. And what that means is that the reflected ray is smaller than the incident ray. Okay? Again, I'm going to provide you with like a multiple choice question. Does the ray continue on? Does the ray go like this? Or does the ray go like that? And you'll have to pick one of the correct choices. This is how you remember what's happening, okay? Water is more dense. So when it hits the water, it bends downwards, okay? The reason for this is because the speed of light is actually slower in water than in air. But I don't want to get into that, okay? Just remember the basics from geometry and just this description and density, okay? Water is more dense than air, so light bends towards the normal. How about this? Okay. Air is less dense than glass. Okay. Air is less dense than glass, so light is going to speed up. Basically, when it hits air, it's going to be bent away from the normal. Away from the normal. And what that means is the angle of refraction, shown here in blue, is going to be larger than the angle of incidence, shown here in white. All right, so more dense towards the normal, less dense away from the normal, okay? That's what you need to remember here. let me finish this lecture and we'll talk about the rest of this stuff next class. I hope this makes sense with these diagrams. Thanks for watching. Please give a like, a thumbs up, and take it easy.